We'd like to thank everybody for joining us for our final webinar of 2023, which is presented by Hakan Sahin, and the title is Ask Me Anything. Take it away, Hakan.
Thank you, Ben, and thank you everyone for joining. Good morning and good afternoon to everyone. As Ben said, today our last webinar, live webinar of this year, and as we did last year, we went through so many different webinars throughout the year, and we decided to have this one as a session where you send us your pre-questions, and we go through them, we answer them as much as we can, and which we will do. And if there's any other questions pending, or if I cannot answer the question due to misunderstanding, whatever the reasons may be, as always, I will give my email address at the end of the presentation. Please don't hesitate to email me or our marketing department, and we can even get on a call and answer as much questions as we can. Having said that, as always, before I do anything, I want to start with the safety moment here. And I read it last night, so I decided I think this will be a perfect time to remind everybody. Holidays coming, we're all excited to go be with our families, loved ones. And AAA says that expected 116 million people will drive close to 50 miles or more from home during the 10 days between December 23 and New Year's. That's a lot of cars and trucks on the road, and I will be one of them. So just a kind reminder, please do not do anything else while driving, but just drive safely and enjoy the holidays. Now today, we grouped the questions, and as we grouped them, this is what we came up with. The first question is related to industrial lead times. Then we have questions about transformer ratings and the load, connections, types of transformers, hydrogen and solar. Interesting questions I received, which is good. So because our industry is changing. And we have a couple questions on liquids that are used in transformers. Having said that, I actually have with me our VP of Sales, Joshua Young, sitting in my office today. I would like him to talk to the lead times. Normally, we keep these webinars to technical questions and technical information exchange only. But because one of our customers asked, then we decided to answer the question. Joshua, go ahead, please.
Good afternoon, everyone. My name is Joshua Yun. I'm Vice President of Sales and Marketing for BTC. Yes, let me address this very interesting question, lead times. Okay, so as everybody have seen, right after COVID, lead time has just skyrocketed. I'm extended to the point where right now is unheard of. So those of you that has been in industry for a long time are probably, we are venturing into territory that we've never seen before. I mean, our transformer now we're quoting something in 2 years out. Okay, and so now question is, first of all, how do we, in general, how do any transformer supplier, okay, maintain competitive lead time, short lead time? So I'm just kind of generically covered that, and then along the way, how we did to we as a company supplier to actually achieve that, maintaining a short lead time. Okay, so in overall scope, 10,000 foot level, in order to maintain short lead time, you got to have three things. Okay, all three things, not 2 out of 3 or 1 out of 3. One, you have to have enough production capacity. I mean, it's no brainer. I mean, can you build it? Do you have capacity? Number one. Number two, even if you have capacity, you can't do anything if you don't have materials. And some of these lead time, some of this critical lead time is 2 years out. Okay. Number three, you have the production capacity, you have the material, but if you don't have design capacity, engineering capacity to actually custom design every one of these transformer, we really cannot do it, right? So these three things go hand to hand, and then and these are all critical in order for any transformer supplier to maintain what we consider competitive lead time. So let's talk about each one. Production capacity, okay? I think in North America, there really hasn't been too many suppliers that come out with extended lead time capacity within the last 2 years. Exception is that we actually opened up a brand new facility in 80,000 square feet the state-of-the-art facility in Chihuahua that produces pen mounts as well as the small and medium part transformers. So with that, we currently have 69,000 MVA production capacity, okay, and in North America, making us one of the largest, okay, suppliers. So that helps tremendously. And then also to help gather more capacity out of this, starting this year, we opened up third shift, which means now all 5 plants across North America are operating 24 hours a day. So that gives us another 25% or so capacity on top of that. But what good is having a capacity if we don't have people? So this is where we kind of struggle, and not just us, but everybody. Okay, the market labor force is very tight in the marketplace. So we actually hire over 1,200 people, 1,200 direct laborers. Okay, these direct laborers are the people actually producing transformer in the plant. Okay, 1,200 people. And then at the same time, another thing that helps us here is we purposely have overlap at all the plants, so that if something happens at one plant, we have ability to quickly load that particular order into another. So that gives us a tremendous flexibility when the order comes, okay, and the customer has no preference from a geographical location wise, we can actually take a look at what's available, which plant happened to have at that time a shorter lead time or shorter lead time, and we can actually level load it at that plant. So it gives us huge flexibility from that perspective. So from a capacity, we made a great stride to enhance that what we have and offer that to the marketplace. Materials, again, although COVID is out, so we're kind of out of the wood, but at the same time, still main critical components such as core steel and other conductors and other still remain very tight. So what we did is that instead of relying on them in a hand-to-mouth situation, we're actually right now, every day, every week, we're maintaining $30 million worth of critical material, okay, in our inventory. And then they're strategically stored at a storage facility next to each of the plants. So we do have ability to pull the material as needed basis. That gives us additional flexibility. Engineering resources, okay. Right now, across the country, a company, we have over 400 engineers. And then on top of that, this year alone, we hire over 120 additional engineers, okay? And not all engineers are in the design department. Many of them are in our production. So our goal is to have 25% of our people actually building the transformer are actually degree engineers that provide technical leadership and then supervision over what we're doing. So we have one of the largest engineering team in the industry. And also, because we've been in business for 50 years, we have 20,000 what we consider done, a proven design. So we don't start from scratch. We use that as reference to get going a lot quicker, okay? And then another thing is that once the design is done, if we need to shift from one plant to another, same design can be accepted at all the plant across the company. So with these 3 things that we have done, that allows us to maintain short lead time. One more thing I want to touch base here is those customer that is looking for, reserving production slot way out in 2027, even 2028, but they don't even have the confirmation exactly what design they need. We are actually having what they call a production slot purchasing program. So it's very simple. You tell us, and at least identify which plant, and give us at least a ballpark understanding of what you need, and we can come up with some kind of budget price. And all you have to do is put a small 15% down payment, and they will secure your slot for that particular month, year. Again, gives you the flexibility. So again, these are some of the things that we were able to come up with to help facilitate, to help ease the pain that the customers and markets been seeing with the lead time.
Thank you very much, Joshua. And the reason why we wanted to get more detail than just showing you our lead times here, because we knew, and we have been getting these questions from so many customers, because lead time right now is very critical. the industry demand has increased and going to increase. It's not going to show any slowdown that we see for at least the next 7 to 10 years. So thank you again, Joshua, for explaining the details behind how we are, as Virginia Georgia Transformers, keeping our lead times shorter to serve our country and our customers. Having said that, now we can go into some technical stuff, and here are the questions. And I did not put the answers, I just put the questions directly on the slides as written by our customers, our listeners here. So this question is from a listener. The utility has received a 69 kV delta to have 13.2 kV grounded Y power substation transformer with high side designation 67 or 69. So I'm going to pause here, and if the person who submitted this question, please email me separately, because I am confused, because the transformer is either 69 kV or very rarely, I have seen him, but very rarely it can be 67 kV. A transformer cannot be 67 or 69. It has to be either or. So I'm going to have to assume that. And I know that it's not like a reconnectable condition or anything like that, because the voltages are extremely close. So I'm going to assume that we're talking about, let's say, a 69 or a 67 kV, maybe two different transformers, and I'm going to answer your questions going forward. Loaded transformers are permitted continuously operate at 5% over voltage. That is correct. Actually, all the way up to 110% over voltage. Not recommended, but we design and build them to be able to withstand that continuous run at even 10%. However, because maybe I am not clear about the question, I wanted to speak a little bit about what defines the nominal system voltage. And it is defined in C57, IEEE standard C57 1200, section 5.5.2. The voltage rating shall be at no load and shall be based on the turns ratio. When a transformer is provided with taps for de-energized operation, they should be at full capacity. So since the 69 kV we are talking about here is the high voltage side, and 99% of the transformers I deal with in the last so many years in this industry have de-energized step changers, you do have the flexibility to go 2.5% per tap. And if your 69 kV is the nominal tap voltage, and you have 2 up and 2 down, then every tap, one tap up will be 2.5% more, another one 2.5% more, or vice versa. You can go down and 2.5% less voltage, and then of course the minimum voltage tap will be 5% less than the nominal system voltage. And table in the same C57 1200, table 3 for class 1 and table 4 for class 2 clearly defines what the nominal system voltage and maximum system voltage, operating system voltages are. But coming back to 5% over voltage, the answer is yes. What I cannot answer correctly here, because I do not understand what it means to have a transformer 67 or 69, but yes, you can operate your transformer at 105 pu no load voltage. Is it recommended? Maybe, maybe not, depends on who you buy your transformer from, but yes, per the standards, we have to design and build them to continuously run all the way up to 110%. With that said, the next bullet point here asks the question, at no load and 10% over voltage permitted, is the 67 kV designated transformer no load rated for 69 something? Once again, please send me an email. I want to understand exactly what we're talking about here. Let's go to the next question here. It says, why does the transformer manufacturer nameplate utility request a 69 kV transformer to be 67 kV? It cannot be. If you wanted a 69 kV transformer, you should have gotten a 69 kV transformer, not a 67 kV transformer. So, and because it's an open question here, I try to explain to what I think I need to answer the question to. I'm going to continue to the next slide, but once again, if the submitter of this question is online, please email me so we can get on a quick call and then answer more. The next one. The question starts with a comment. We are designing a project which has several constraints due to its location, regulations, equipment availability, etc. A large-size electric boiler plant needs to be powered from a 13.8 kV utility source. The largest transformer permitted by the utility is 7.5 MVA. Okay, I don't know why they would just do that, but let's go with that. There will be 5 11 megawatt electric boilers. So I think the total energy needed is 55 megawatts, right? So you're only limited with having all the way up to 7.5 MVA. And it says here they'll be operating at full load for most of the time, even in summer. The transformer will be indoors, inside an existing building, and the available space is limited. I'm thinking of paralleling 2 transformers for each boiler to meet the 11 megawatt continuous demand of each 6.6 kV electric boiler. Yeah, but if your maximum size of the transformer is 7.5 and you parallel 2, I don't know if you'll be able to get up to 55 megawatt, but that's your decision. I'm a transformer guy, not really the whole substation understanding here. What I will do, though, I will answer your questions. Is KFWF design economically feasible, or do we need to use the conventional KNF design for this application? So for those listeners here who may not know what KF and KN is, let me answer that real quickly. K, the first letter, stands for the insulating fluid. And when it is K, it is the insulating fluid with fire point over 300 degrees C. F stands for forced circulation through cooling equipment, such as cooling pumps, natural convection flow in the windings, non-directed flow. Okay, let's be careful, non-directed, because there is a follow-up question on this one about the directed flow, and I'll answer that. And then W stands for water, and then the last letter F stands for forced circulation, such as fans, pumps, water. So let's continue before I answer that question, because the answer to each question is one, okay? OFWF design will help reduce mechanical ventilation needs while potentially reducing the size. So let me quickly explain OFWF. In this case, the first letter O stands for insulating liquid with fire point less than 300 degrees, okay? And the rest of them, FWF, is still the same as the forced circulation, water pumped, and of course the forced circulation of the fans and everything else. So with that said, it continues. This design should also elongate the life of the transformer, as we'll have dependable, stable water with the design temperature entering the cooler, heat exchange, and water cycle. I'm thinking of a single cooling water heater header for the anticipated 12 transformers. How can I get technical support from VTC to discuss this application? So the answer is very long. So once again, it really depends. We need to understand exactly the location. You know, you can do either or. Really, it's up to you. We'll have to get more information. We'll have to do what we call it a quotation design to give you from a price perspective, so you can compare the prices between the two KF design or OF design, and we can actually share with you, learn from you first, your loading, especially how you're going to cool. You already mentioned above that space is limited, it's enclosed, so obviously there's not enough air circulation, which is why correctly you are thinking about cooling the inside, the windings, by forcing some coolant, such as water in this case. So, but as a general answer for other listeners here, what I wanted to do is I wanted to share the explanations of the differences between oil, K, you know, if you want it over 300 degree, fire point or less than 300-degree fire point. It all goes with the safety requirements and regulations that you have, and the area that this transformer is going to be, the loading and the cooling requirements. So please email me separately, and this one I will need to set up a meeting with the submitter of this question, and we'll have to get into much longer discussions. First, we have to get more details so we can help you. But yes, we'll be more than happy to help you in a separate meeting to answer this question. The next one. Do you have a noise data table for 1500 kVA and larger transformers humming? I like that word. Liquid as well as dry at 75 and 100% load. We don't, because we follow the standards, and NEMA standards do, of course. However, I do want to talk about IEEE standards. Under C57-1290 section 13, our industry experts in the last 7 to 8 years or so have done tremendous study and updated the noise, the sound level test section under 1290. Tremendous information is in there. And I strongly recommend for you to really look and study section 13 under C57-1290. You'll find a lot of information there. Why am I speaking about? Because the load noise, we knew about the load noise, but IEEE standards didn't really have load noise until the latest revisions. We have it there now, and we put it there. We have a lot of technical calculations, examples, and everything else that shows the sound levels, sound pressure levels, and everything else. For those of you who may not be familiar with where the sound is coming from, the sound, especially for smaller transformers, because there's a number here in this question, says 1500 kVA. You know, back in the days, we used to, especially smaller transformers, we will do only no loss sound test, because the core is known to be the originator in the transformer noise, and the transformer core transmits these vibrations of the core through the dielectric fluid and the structural supports to the tank. However, as the transformer size gets larger and larger, I don't know, say above 30, 40, 50 MVA transformers, and especially when you get close to 100 and 200 MVA transformers, we know that there is actually a load noise as well. And the load noise is produced by the vibrations of the windings and tank walls when the transformer is loaded. And there is a third element to sound of transformers. And that third element is from the cooling devices, like the fans or the pumps. So the total audible sound of a transformer is now, per the standards, considered to be the sum of all three components: the core, the load, and the auxiliary cooling devices audio. All combined together is the sound level. And as I said, the levels, acceptable noise levels, are in the NEMA standards. However, even if you get a copy of the NEMA standards, you are not going to be able to find a different table for 75% load versus 100% load, which is why I explained and I recommended for you to study section 13 under C57-1290, the latest revision that was released in 2021, because in there you will find calculation methods where you can actually calculate, we can calculate with you if you don't want to do it yourself, where you can calculate the load noise for different loads. I hope that answers the question, and I'm going into the next one. This one, scenario from one of our customers says, my operating load is 75% of the transformer kVA rating without fan cooling, but my connected load is equal to 100% of the transformer kVA rating with fan cooling. Okay. In your experience, have you seen an engineer use fan cool ratings of a transformer to run continuously to achieve 100% of connected load on the transformer in real-world applications. So the loading and the cooling, really, what is happening in the transformer when you're loading a transformer? As we all know, the losses, which turns into temperature heat, right? So we have to be controlled by these fans, the pumps, whatever the cooling method that we use. All we are trying to do, depending on the load changes, we are trying to make sure that the winding temperature, average winding temperature rise, and the average top oil temperature rise stays below the required levels. IEEE standard says the average winding temperature rise shall be 65 degrees. We used to have it 55, 65. You still can specify it that way if you want to, but if you don't, it's 65. And when you add the ambient temperature of 20 degrees, then 65 plus, known average ambient temperature is 30, 65 plus 30 is 95 degrees. And as I said in my previous webinars before, the reason why 95, we want to keep everything below 100 is because we don't want to get past 100 and start degrading the insulation, because then the water, the tiny amounts of moisture in the insulation will start breaking down. So having said that, here the question is talking about fan cooling. Can I run it at 100? It is really going to be connected to these gauges, temperature gauges, or your automatic controls to run the fans or your pumps. It's going to read from the temperature of the winding and the temperature of the oil. Of course, winding temperature, if you have fiber optics, then it will read directly from the winding itself. If you don't have fiber optics in your windings, then it will be a simulated load with the winding WTI-CT, winding temperature indicator CT, current transformer on one of your bushings. It will read the amount of current, and we have already programmed, depending on the current, CT will tell the winding temperature gauge what the temperature is. So that gauge, when it gets to, say, 85 degrees, 65, depending on how we set it up, it's going to start your cooling devices. It's going to start your fans. It's going to start your pumps and other things. The same thing with the top oil temperature. Okay? So what I am getting to here is the answer here is really depends on the gauge and how the gauges are programmed to turn the cooling devices on or off. And that goes with the loading of the transformer itself. Going into the next question here, and this is related to connections. Why do some manufacturers not show in the schematics and or wiring diagrams the CT feed-through connections? During the drawing review of a vendor drawings, I have had to request the CT feed-through details to be added to the substation drawing. Very good comment. Let me first explain for those who may not know what we're talking about here. First of all, CT stands for current transformer, and depend on really what you're going to do with these CTs in the field, in the substation, for your protections and whatever else you want, we put the CTs that you want us to put in your transformer. Then we take the CTs, these can be mostly bushing mounted, inside the tank or outside the tank, depends on the application. Nonetheless, the output of the CTs first, if they were inside the tank, bushing mounted CTs as an example, let's take a simple example here. So the CTs are mounted on the inside the tank and the bushing goes through these CTs. The output of the CT cables now running inside the tank comes to a feed through, and this feed through we connect, take the output of the C2 and run it through a conduit and bring it from this feed through down to the control cabinet. Okay, and then when you receive the transformer, you connect to this control cabinet to terminal blocks, and you do whatever you want to do with these CTs. And what, now let me answer the question after the explanation, why some manufacturers may not be giving this. Because maybe the reason, we know suppliers, transformer suppliers know that when you receive the transformer, you will be connecting your CT outputs from the terminal blocks in the control cabinet. You're not going to have to go on top of the transformer or on the side top somewhere, wherever this feed through is. You're not going to need to make any connections there, okay? And only connections you're going to make will be from the control cabinet. That may be the reason. I cannot speak for why and why not for others, but I have to use my best judgment to answer the question. That may be the reason, because you don't need to do anything in the feed through. However, I do understand why the submitter of this question would like to have the CT feed through connection diagram also, because nobody's perfect. Everybody may make mistakes. What if you receive the transformer and you're testing the CTs and you're finding out that the CTs aren't really wired correctly per the diagram, the drawing that shows, and you want to troubleshoot it? One of the first things that you want to troubleshoot, make sure that the wire that's running from the CT feed through, say from the top of the tank to the control cabinet, it is not swapped accidentally. That's probably why it is important for you to have that CT feed through connection on the drawing. I agree with the submitter, it should be submitted. However, why they don't submit it, maybe because they don't want to have a confusion of, because the feed throughs will have, say, sometimes 30, 36 pins on it. However, the terminal blocks will have only 6 per CT. To avoid the confusion, that's probably why they don't do that. That's my assumption. Next one. Could you please indicate what and how some transformer connections remove even harmonics? Well, the first thing I'm going to say before I explain some, I don't know if it was this year or last year, we did a presentation, and please email me and I will be more than happy to email you the presentation on harmonics. Very much a lot of detail we have in that presentation, so I'll be more than happy to email you that presentation. But since the question is here, let me talk to it a little bit. Harmonics are distortions in the voltage and the current waveforms, and they are caused by the nonlinear loads, such as electronic devices, variable speed drives, or arc furnaces. And these harmonics actually create overheating and insulation degradation. We can use rectifier circuits, and these are actually explained not only in our presentation, but also C57.18.10. And in that IEEE guide, it actually shows the proper ties of more common circuits. So that will, some of the answers you may find in C57.18.10. But what we also do is, just because we are transformer people, when you tell us the harmonics that this transformer is going to operate with, we consider the increase in the losses in the windings, and then we recommend to derate or design it with higher MVA, and we pay attention to the winding rise calculations. We also give additional clearances to overcome the increase in stray losses. Because as I said, when the harmonics distort the voltage and the current waveforms, then it will actually act like it's increasing the voltage and sometimes even the current inside the transformer. So hence, because of that, we actually will increase some of the clearances face to face, or even lead to tank clearances. And then we also end up lowering the flux density, kind of like connected to that 10% over voltage thing, because when the harmonics are too much, then the voltage of the transformer will act as it's increasing. And to overcome that, we actually decrease the flux density to allow the transformer operate without any issues at higher voltages. But like I said, please email me. We have a full-blown presentation on harmonics, and I'll be happy to email you that presentation. Going into next one. Does Virginia Transformer manufacture PV transformers, specifically Y to Y? I'm not good with acronyms, but I'm going to have to assume the PV transformer stands for photovoltaic step-up transformer. If that is the case, because I'm sure that the submitter of this question is not asking just simply, can we do YY transformer? Because the answer to that is very simple. Yes, of course we can do YY, we can do Y delta, delta Y, whatever you want. But I'm going to have to once again assume that we're talking about photovoltaic step-up transformers. If that's the case, then no, the photovoltaic transformers is high side will be delta and the low side will be split Y. So it's going to have two Ys on the low side with a high side delta. If so, once again, there's actually a guide, C57-159, guide for application in DPV power generation systems. So it's very valuable. I had to study that because I had to get back to photovoltaic step-up transformers last night when I was getting ready for this webinar. Very good information is in that. However, if the question is not related to photovoltaic step-up transformers, then yes, of course, we can do YY, delta Y, any connections you want. And then, of course, we follow the connections section under C57-1200. Going into next one, this, I don't really, I mean, the question seems extremely simple to me, but I'm sure there's more to it. And you may, the submitter of this question, please get back with me. Are delta-delta transformers ever used? The answer is yes. But I'm sure there's more to this question, so please email me. I'll share my email at the end. Of course, delta-delta, delta-Y, YY, they are used every day. This one is a good question. They're all good questions, right? What are zigzag transformers and what are their uses and applications? And I actually put the questions exactly submitted to me. So if this diagram doesn't apply to a zigzag, please don't say that, Hakan, you don't know, this is not zigzag. I'm just taking it, putting it directly on the screen here. So what is a zigzag transformer? A zigzag transformer is a special purpose transformer where the winding ends connected as interconnected star. It's like this. Just think about a simple delta Y transformer, okay? And the low voltage side, you know, you have a start and a finish. You take the finishes and then you make neutral, and you take the starts, depends on the, you know, vector and group, and then you take them to the bushings and it becomes, you know, X1, X2, X3, and XO. In zigzag transformers, each output is a vector sum of the two phases offsetting each other by 120 degrees. So what we do is, on each leg, you actually have, in a way, two different, I'll explain that in a minute. Let's talk about the uses of zigzag transformers, okay? So as I said, these are connected, interconnected star, that each output is the vector sum of the two phases offset by 120 degrees. What is it used for? It is used as grounding transformer, creating a missing neutral connection from an ungrounded three-phase system to permit the grounding of that neutral to an earth reference point. The reason for that is to perform harmonic mitigation, as they can suppress triplet harmonic currents, to supply a three-phase power as an auto transformer, serving as the primary and secondary with no isolated circuits, and to supply non-standard phase shifted three-phase power. So really, if you have an ungrounded system and you want to ground it with the harmonic mitigation, that is the uses of zigzag transformers. How they are designed is the first coil on each zigzag winding core is connected to the contravise to the second coil on the next core. The second coils are then all tied together to form the neutral, and the phases are connected to the primary coils. And each phase therefore couples with each other phase, and the voltages cancel each other. And there will be negligible current through the neutral point, as zigzag has a high positive and negative sequence impedance with a low zero sequence impedance, which can be tied to ground. So that's what the zigzag transformer is, and that's the application of the zigzag transformer. In your experience, our large VFD stands for variable frequency drive. Now, once again, those listeners, when you ask me questions, I am not good with acronyms. I'm just going to have to assume the acronyms as well as I can. So next time, please do me a favor and just try not to use the acronyms, please, just to make sure that we are speaking the same language. But anyway, our large VFD is often supplied with phase shifting transformers. Yes, it can be, and it can be done so to help with the harmonics distortion. Second question is, are the requirements of phase shifting transformers typically provided to you by the VFD manufacturers? No, the requirements for phase shifting transformers are supplied to us by whoever is purchasing the transformer. So what the purchaser is going to have to do is to get together with the VFD manufacturer, define what you want the phase shifting transformer to be like, and then give us the requirement finally. So we don't have to get in touch with the VFD supplier manufacturer separately without, you know, we like to have only one spec, one requirement coming from the transformer purchaser themselves. Going into next. What is the rule of thumb to specify phase shifting transformers for XX number of pulse VFDs? Controls power flow through the specific lines, creates a force onto the power transmission networks. Now, these are, I don't know if I should say rule of thumbs. I guess rule of thumb will be a good one. And then phase shifting transformers also creates a phase shift between the primaries and the secondary side. And depending on the power transfer nodes to be connected, I'm sure the submitter of this question knows better than I do what the phase shifting transformers are used for, right? They are used to connect the two nodes with different phases. And many varieties will be existing, and there's so much. Really, if you look at, I think even IEEE has a guide. If not, there's a lot of literature on phase shifting transformers that shows so many different connections that we can achieve. Depends on, once again, the shifting that's required and the nodes that this transformer is going to connect. And one of the other maybe rule of thumbs, I guess you can say, that we need to follow will be the impedance needs to be as low as possible to lower the no-load phase angle. So these are the basics. The second question is, are there special routine tests for phase shifting transformers? As far as I know, it's standard IEEE tests that are defined in the IEEE 1200, 1290. One addition is Hidron, even though it may not be a routine, but Hidron is a highly recommended test to be performed on every phase shifting transformer, just to ensure that you don't have any heating and all these different connections inside the transformer. Next one. Hydrogen and solar. Which rectifier manufacturers have you worked with and supplied transformers to for electrolyzer rectifiers? And this is something that's becoming a big thing. Unfortunately, I cannot give names of our manufacturers that we work with. It wouldn't be a right thing for confidentiality purposes. So I'm gonna, but we do work with many of them. We have a lot of requests for quotations from different hydrogen generation plants that are really popping up everywhere. Next one. For solar projects, we typically size main transformers based on the total inverter nameplate rating, such as that the top rating of transformers higher than the total inverter. However, we have recently spoken with some engineers who have sized main transformers based on the export capacity of the project, such as that the top rating is higher than the export capacity. Our method results in a larger transformer, and we are concerned we are being too conservative and increasing the project costs unnecessarily. Please provide any insight you can. What do you typically see? Well, with my almost 30-year experience, I'm old school. You ask my inside opinion, I'll give you my inside opinion. You're not being conservative. It's good to be conservative on transformers, because what are you going to do? Save 10% on the initial price and then pay for it later? I would rather pay a little more at the beginning, because especially now we're talking about solars and all that. You got to remember the reverse power flow as well. So I believe, this is my humble opinion, I may be right, I may be wrong, but I think you're doing the right thing, especially considering the reverse power flow that these transformers are going to see in these applications. Oil. I have seen split between manufacturers in oil impregnation during and after a vapor phase dry out. Traditionally, this is good. It's I'm going to summarize here. Pretty much what it's talking about, the question is talking about here is when we dry the transformers in vapor phase, okay, during and maybe after the vapor phase process, we actually do oil soaking, or as it says here, hot oil impregnation prior to final vacuum. And I'm assuming here that final vacuum is the final vacuum process during the VPD, not the final vacuum after tanking. After several decades, some manufacturers have now switched to the first oil impregnation after the final sizing process, followed by a vacuum and hot oil filling after tanking. Yes, there are different methods, and there are actually still suppliers, and depends on the size of the transformers. There's some plants maybe still not even using VPD, just using conventional dry oven. There are some differences in philosophy here. A concern is that the insulation shrinks a bit after the first impregnation, and the final sizing may be inadequate if the insulation has not been impregnated first. Others believe that the insulation has dried adequately for sizing after the first impregnation. Each process is advocates, and the time for final sizing and has plenty to do with the best process. You are absolutely correct. Is there any advantage to either process? Depends, really. As you said here in the last part here, the whole idea of drying an active part core and coil is to get the moisture content in the insulation less than 0.5%. Okay, vapor phase is known to be the best process to achieve that. Oil impregnation, the advantage of oil impregnation during vapor phase is, once you remove the active part from the vapor phase, there is that final pressing of the winding, applying the jacking pressure on the coils and then securing the coils using the core clamps and keeping them under pressure. And then take that active part, go in the tank, or if it's a bell tank, put it at the base and then put the tank around it. Nonetheless, all this takes time, especially if it's a large LTC load tap changing transformer. Say, imagine a 200 MVA LTC transformer. All that process takes time. So when that takes time, we will have surface moisture. It may take 10 hours, 12 hours, 18, 24. I don't know, depend on the plant. So how do you take that surface moisture out? Yeah, after you perform tanking, you put the cover, you welded the cover. Now you're going to go under vacuum again. At that time, just vacuum may not be enough, especially for large transformers. So some suppliers, some manufacturers, they do hot oil spraying even after tanking the active part. So once again, the answer really here all depends to that what are we trying to achieve at the end? What we are trying to achieve is less than 0.5% moisture in insulation. And I think that answers the last question. Is the resulting moisture in the paper press but only marginal difference between the two processes? It's more about how the process is conducted correctly than the process itself. Going in on oil, is Envirotherm FR3 considered less flammable? I think the answer is yes. Once again, these names are brand names, so I don't want to speak to any brands, but their websites have a lot of really good information. You can go into their websites and get more. I don't want to speak for these names, brands per se. But of course, as we all know, why did we have to come up with biodegradable oils? Two reasons. One was their fire point is higher than mineral oil. And of course, the second reason why we had to come up with this biodegradable oils is because they are biodegradable. So if yes, the second question is, does it require firewall between transformer and between the transformer and the buildings? That's really your site safety regulations. I cannot answer that. I don't want to answer that and give any information, and then I don't want to, it goes into safety regulations, so I will leave that up to you. Please follow the safety regulations and rules that's required. Just because you have a transformer with biodegradable oil doesn't mean that it's not going to catch on fire. It may. So please be safe on that manner. Does it require oil containment? Well, once again, I'm not a substation guy, but just because it's not biodegradable doesn't mean that you don't need to contain the oil. I would prefer, if I was designing that substation, to still have an oil containment regardless what type of oil that I am using in my transformer. What is corrosive sulfur? Good question. I'm going to do a little check. I think this is the last slide. Yep, that's the last slide. So I'll take my time and answer that. What is corrosive sulfur in power transformer oil analysis? So let me answer what is corrosive sulfur first. There are different types of sulfur components found in the refined transformer oil, but not all types are considered to be corrosive. Elemental sulfur and sulfur compounds in concentrations all the way up to 20% are present in the crude oil. There are 5 basic groups to sulfur and sulfur compounds found in the crude oil. And the reason for that is because sulfur is 0.05% of the Earth's crust. Some sulfur compounds can actually aid in the oxidation of the oil. And also some sulfur compounds can act as metal passivators and deactivators, and reducing the catalytic effect of oil oxidation. Oil suppliers, during the refining process of the oil, they try to remove many of these corrosive sulfur species to make it more stable compounds. But not always they may be successful, and they may not be able to successfully remove all these sulfur species from the oil, which is, oil is, mineral oil is coming from the earth. So when they take it, it's already got sulfur, so they try to remove it. And they may not be successful 100% of the time, and some small quantities may be left behind. So that's where it's coming from. Corrosive and reactive sulfur compounds can react on contact with copper and other metals. Copper and aluminum is least resistance to sulfur. And what it does is it actually forms copper sulfide. Even if the transformer is fully, there's no oxygen, it's under nitrogen blanket, it's fully enclosed, you may, if you have sulfur in the oil, you will still have these formations of copper sulfide. If your winding material is copper, or if it's aluminum, you'll have aluminum sulfide. And if there is oxygen, say that accidentally your transformer is free breathing and you didn't pay attention and you have a lot of oxygen in your transformer, you didn't process it, vacuum fill it correctly. And if the oxygen is there, more compounds will form. A lot more compounds will form. There's actually really good literature on that. I actually was part of a study years ago in another supplier where we had corrosive sulfur issues coming from something else. I cannot give all the details here. But the transformers that we brought back from the field after failure, and it was not good to have those issues, but it was good as a learning and being able to see in person the color of this copper, how it changed to green and blue in a way, because of this oxidation and copper sulfide formation around the conductor. So what it does is it causes corrosion of the metal surfaces, especially on the exposed copper surfaces like the no-load tap changer contacts. So if the copper is more exposed and you have sulfur in the oil, then you will have this copper sulfide buildup, and you'll have bad contacts, and you'll have bad conductivity of the metal. Worst case is, imagine your winding conductor paper wrapped, and you have now copper sulfide building up. What this does to insulation, the paper, is it starts degrading the paper because of copper sulfide, because all of a sudden the paper, which is supposed to be just cellulosic material soaked in oil, now it's got copper sulfide in it. So what happens to the dielectric strand of that paper? Obviously it reduces. So in a nutshell, that's what corrosive sulfur is. Back in the days, some people thought that using Fuller's earth, pretty much clay, and running the oil through Fuller's earth, clay mud, pretty much, will take care of the sulfur. It does not. That may help with the interfacial tension of the oil, but not the sulfur. So the answer to that question is, how can it be fixed? The true solution is for you to remove that oil, dispose it, and then flush inside the tank if the damage is not too much already, okay? You may be at a case where the damage may be too far gone, and I don't know if you want to really spend all that money. But if it's not, dispose that oil, get rid of it, flush the inside, the core and coils, the active part, as good as you can with clean oil, dispose that oil, and vacuum fill the transformer with clean, filtered and non-corrosive sulfur oil. That's really the only true solution to if you have a corrosive sulfur problem in your oil. Having said that, before, I know we are out of time, but once again, thank you for attending. I'm going to ask Ben in a minute if we have any additional questions. If not, before we lose others, here is our emails. You can email at marketing@vatransformer.com, or you're very welcome to email me directly at hakan.sahin@gatransformer. Please pay attention, it's not VA. I'm special, it's gatransformer.com. So please email, and we'll be more than happy to answer. And those 2-3 slides where I said, please get in touch with me, please do so. Ben, do we have any questions?
I do have one here, Hakan. Let's see. It says, do we need to store spare bushings vertical, OIP bushings? I guess that means the two different types of bushings. So should they be store spare bushings vertical?
Yes, good question. The answer is yes. Depends on the time, of course, but if you're going to store it more than 3-4 months, the answer is yes, please. Because what happens is, if you store it horizontally, then the area, that half of the area that's not going to be soaked in oil, is eventually will degrade over time. So if you're going to store it more than 2-3 months, yes, please store it vertically. Any other questions, Ben?
Let's see. I have more of a comment here, not really a question. Comment on 67 kV. I did not submit the question, but do have insight. In the Western United States, I have seen a 67 kV high side rating on many old substation sub-transmission auto transformers.
Okay.
Uh,
Okay. Well, like I said, I would like to speak more with the submitter of that question so that I can understand, and if I can be helpful to answer it, I'll be more than happy to answer it. And having said that, it's 1 p.m. Thank you so much, everyone, for attending, and look forward to our new list of webinars coming next year. Thank you so much.